So today I want to talk a little bit about tangent lines and local linearity. We've kind of started discussing tangent lines a little bit, and you're probably familiar with them from before dealing in geometry and algebra 2, but I want to talk about them a little bit more. Well, a tangent line is just a line that touches a curve at least one single point. And you're going to understand in a moment why I say at least one. So if I'm looking here at this parabola, it's not very pretty, but it does exist. If I want to draw a tangent line, let's say that this point right here is called C, I'm going to have a line that looks something like this. That tangent touches at just one point. But if I have a point right here, and I'm going to call that P, I guess, and I draw a tangent line, well, that touches at one point at P, but it's also touching here and here. So the tangent line really should be thought of as a line adjacent to a curve that best approximates the slope of that curve. So any function with a defined slope at a specific point will have one and only one tangent line at that point. What does that mean? It means that I can't just keep drawing tangent line after tangent line after tangent line. You know, I can't go like this and then this and then this. There's just one tangent line. There's one tangent line at a point, and that's something important to remember. Now, when we're talking about tangent lines, we also have kind of different specific special situations. So if we have a turning point, a maximum or a minimum, our tangent line is just 0, or you can think of it as being horizontal, and I'll kind of show you what that means. So I can actually use that parabola again that we had up here. Here I've got this turning point, which is actually a maximum. The tangent line there is going to be horizontal with a slope of 0. If we have a point of inflection, that where concavity changes, so if we had something looks kind of like this, right, we have a point of inflection right here. Well, the tangent line right there, and this is so hard to draw, maybe here would be a little bit better, but it would be vertical, which right there it's really not quite vertical, or 0. So it would be is vertical, or, and actually 0, or it's just undefined, right? Or 0, or it's undefined. It would have an undefined slope, right? Now, if there's a sharp corner or a cusp, the tangent line does not exist. That would be if we had like an absolute value function. You're familiar with that. Or if you had a function that looked something like this, that's like a cusp. There is no tangent line there. It does not actually exist. And the point on a linear function, the tangent line is just actually the same slope as the line itself. It's the same slope as the line. And that looks kind of funny, but if you have a graph and then you draw a linear function, well, the tangent line is just itself again. You can see I kind of tried to draw it a little bit separate, but I think that it's really just kind of understood. It's basically the same line. So when we're talking about writing equations of tangent lines, we're just going to write them exactly the same way that we would write a linear function. So you're familiar with slope-intercept form. I'll remind you of it. Slope-intercept form is in the form y equals mx plus b. You can probably say that in your sleep. And you're also familiar with point-slope form. Point-slope form is the form y minus y sub 1 equals m times x minus x sub 1. Oops. Minus x sub 1. And this point-slope form, that's really what we're going to be using in calculus quite a bit. You can rewrite this, and it's actually preferable that you rewrite it as y equals m times x minus x sub 1 plus y sub 1 to kind of put it in that slope-intercept form, but slope or point-slope form is really what we're going to be using to actually calculate these. So let's try and work through some of this. We want to consider the radical function y equals the square root of x. The slope or general derivative of this function at any given value of x is in its domain is represented by f prime of x equals 1 over 2 radical x. This here is the derivative, and this is what we're working towards. This is what we'll be talking about next. But let's deal with this first. We want to find the slope of f of x at radical x of f of x equals the square root of x at x equals 9, excuse me. Well, in order to do that, all we're going to do is use this slope formula, f prime of, and we're going to find it at 9. So f prime of 9 is equal to 1 over 2 times the square root of 9, 1 over 2 times 3, which equals 1/6. So the slope of the tangent line there would be 1/6. Now we want to write an equation for the local linearization of f near x equals 9. Well, what is local linearization? We talked about that before. That's when we have, like, if we're zooming in closer and closer and closer and closer and closer to that tangent line, and I kind of draw like a close-up version of it, local linearization is where that tangent line is being used to estimate between there. So let's write that equation. An equation here is going to be y minus, or y equals 1/6 times x minus 9 plus 3. Now, how did we get that? Well, in order to get that, first, we had to find what our point was. So we had x is 9. So when x is 9, y is equal to the square root of 9, which equals 3. So the point we're using here is 9, 3, right? And in order to get this, we're going to have y minus 3 equals 1/6. That's our m, times x minus 9 plus, not plus 3. You can see, though, that I add 3 over here to get this, right? So let's use this to actually estimate the value of the square root of 9.1. Well, in order to do that, what would 9.1 be? I'm going to use this formula. So y would equal 1/6 times 9.1 minus 9 plus 3, which is just going to be y equals 1/6 times 0.1 plus 3. 1/6 is 0.66666 repeating, right? And times 0.1, we're going to get y equals 0.0166667 plus 3. So this just equals 3.016666667, something kind of like that. All right, so now let's graph this function and its tangent line at x equals 9. Well, I've actually already graphed the function for us, but now I'm going to graph our tangent line. Well, 9 is right here, right? 9 is right here. And in order to graph this tangent line, I'm just going to draw something kind of like this. Now, this is really ugly, and I probably should have used a straight edge, but I think you get the idea. And what we need it for is part E here. Explain whether the answer to C is an over or an underestimate for the actual graph of the square root of 9.1, and justify using the graph. Well, this is concave down. Our graph here is concave down. So the estimate is going to be an overestimate because our tangent line is above the function. You can see that. Right here, we're writing just on top of the function, so our estimate isn't quite as exact as the function itself. So this is an overestimate because the tangent line lies above the function f of x. So now let's actually find the true value of the square root of 9.1. I'm going to go to my calculator, and I've actually already put in the square root of x, and if I graph this, it's been graphed, and I trace 9.1, I get y equals 3.0166206. Y equals 3.0166206. And if you look here, it's kind of hard for me to show you both at once. You can kind of see at the top and the bottom of the page here. 3.0166206, 3.016666667. These are pretty close to one another, right? So we don't have the exact answer here in our estimate, but we did get very, very close. And when we're doing the AP exam, we only need to use 3 decimal places. So actually here we got incredibly close. So our estimate is working and our tangent line really is useful. So finally, would our linear approximation bee formula also be an accurate tool to measure the square root of 25? Why or why not? I want you to take 1 second and think about that. Pause. Okay, come on back. Why would this be appropriate, yes or no? Well, hopefully you thought about it a little bit and you came up with the answer no. This would not be appropriate because it's too far away from radical 9, right? So radical 25 is too far away from the point of tangent line, from our tangent line. I'll just write tangent line. Because if we were going to use radical 25 is somewhere out here, we're going to want to have a more accurate tangent line in order to get an accurate estimate around there. So hopefully that makes sense to you. Any questions that you have, please leave in the comments, and I will answer them during class, and I look forward to seeing you soon. Bye!